So, good morning, everybody. I'm Kshitij Kumar. My ID number is 23408189. I'm from January intake 2025 MSc in Cloud Computing NCI. Here, I will be presenting my Fog and Edge Computing uh, semester 2 project, which is where we are going to simulate, where we are supposed to simulate simulate based upon a proposal from a research paper. Here I will be mentioning our research question and I will be continuing with the presentation. So for the introduction, as we all know that these days the major issue with data that came with cloud was actually three V's, which were like volume, velocity, and variety. So to tackle these three V's, we have started to use edge and fog computing. So this paper that I will be using does tackle that exact same thing using a scenario where a camera and a different type of sensors uh, get processed into a edge environment rather than any type of fog environment. So how does that work? We'll just go through it. So yeah, first of all, yes, IoT growth has led to volume of data as I just mentioned. Traditional cloud-based architecture is not that useful. Reason being, a lot of data is coming which might be of different variety and does not even be verified. So it can be quite useless, or it can actually just be eventually be dumped, but does take a lot of computational power. So that's why such architectures are important. And fog and edge technologies these days is basically used to make sure that the computational power that requires to do all the processing is as close as to the user rather than to the central server. So yeah, the goal is just going to be demonstrate this. Actually, go through this for now. So the research paper that I have taken is name is a new edge computing architecture for IoT and multimedia data management. Reason being why multimedia? Multimedia is basically referring to multimedia devices like cameras and sensors, as they require a very high amount of processing. So let's say a camera that's live in our college itself, we cannot just host the processing part onto the AWS EC2 because there are, let's say, 100 cameras. Every video will take like quite a quite a lot of computational power just to be processed. So that's not really cost effective rather than just actually processing it over the edge. For example, we can install a very small uh, CPU, you can say, or very small system to inside the camera or to the nearest hop, which can be like a central server inside our college itself, which can be used as a fog server that eventually will connect to a cloud. But yeah, that's a system that we are actually just presenting here. Again, its focus does comes with reducing the latency and efficiency of, with such architecture. So for the system design, again, I've three different layers are there as just mentioned: IoT devices, fog nodes, and cloud servers. IoT devices are your sensors and cameras. Fog nodes are your central server or one up away from the IoT devices. Um, that I would not say work as a central server, but yeah, you can say for a localized environment, it can act as a central server. And then there is eventually a cloud server, which is like core central server. So yeah, as I've mentioned there as well, process module for analysis is cloud aggregation and storage. Okay, we'll go through it. And principles are process early and process locally, transmit less. So yeah, these are the core fundamentals that we will be just applying. So what else we have done? We have simulated wireless technology, assuming uh, we have assumed that we are using a Wi-Fi connectivity, which is like 5G Wi-Fi connectivity, and latency and bandwidth parameters turned to mimic real life, real world performances, represents realistic multimedia streaming conditions. So we how we have implemented it? We have implemented it this this architecture simulation using Java iFoxSim, created fog devices for cloud edge and IoT cameras. So yeah, it's basically it's basically inside there are a lot of functions for sensors and for devices, fog devices. So that's what we have used. There are just a lot of modules, packages inside the iFoxSim. We can just download that stuff as well. It comes with iFoxim. Then we have added some sensors and cameras as just mentioned, then displays. So for display in the code itself, it says this word that actuators. Like I can be wrong while pronouncing it, but yeah, that's just display. It does comes it does have a different file. It's in the entity file itself. Then we have defined application modules and data flow. Okay, we have defined that stuff and use deterministic distribution for periodic data generation. So after this simulation that I've attached with the presentation itself in my report, so the matrix that actually came out was the cloud was spending 28,000 word per second. The edge was 122,100,000 122,100,000 if that's how you pronounce it, and cameras were like 200,000 volts for each camera. The reason for that was that is we have actually as I said that we are not prioritizing what we wanted to do. We wanted to reduce the processing power that goes into the cloud to minimize that and make it as near as to the edge itself for like the IoT device itself. So where the camera took the most load, why processing all these stuff as the camera is the most localized um or the most closest to the source of the data generation, and eventually it becomes it in the cloud as the data gets filtered and eventually goes to it. So that's how the simulation works. Yeah, that's what we have done here. And for the discussion and limitations for this project, it validation is processing at the edge reduces the cloud dependency and improve latency. That's true. I just showed you the matrix X. So the cloud dependency is extremely low as the most of the processing does go into the cameras itself, and eventually we can even just remove the cloud and have a very small data center at the local end, and can eventually store all the process data into that. And if required, a small fork server, because it's not requiring too much into the other parts other than the IoT device itself, because we are making it localized. That's what the paper proposed. Then the limitations. Let's talk about limitation and what are the things that we could have actually implemented here. So iFoxim does not model realistic wireless network behavior. So like packet loss and jitter or higher ping or a lot of traffic. There are just so many conditions, or sometimes even your Wi-Fi just turns off, the you completely lost the connectivity. So with iFoxM, these conditions are not really possible. It's less flexible with the framework itself. There, I believe there are just I was searching for it. There are more frameworks. Like there's something yet another simulation something there's that's another python based tool that gives you a lot more flexibility with these conditions, actually applying these conditions. Then we have 5G performance approximated, not simulated. So for this, it's like I cannot simulate that. If I have a 5G Wi-Fi in real life, it fluctuates. So it's like whatever the 5G, let's say the approximated, it's 100 Mbps. So that's what we just went for, rather than actually just simulating it, because it cannot be simulated in actual world. Then future work, the things that we will try to implement that integrate network simulations, because network simulation eventually can be created. It's just going to be quite complex, and I just told you that there are better frameworks as well. So we might be able to try something, because I heard that those frameworks are just a little bit different from what we generally do. Then add AI based dynamic model placement and model mobility of IoT devices. So these are a few limitation and the future work that we will be trying. Conclusion and future work. So I just mentioned the future work. For the conclusion, fog and edge computational can significantly reduce latency and bandwidth, as I just mentioned. That the more localized it, the more near to the IoT device or the data where it's getting produced, the faster it's going to be, and the easier, the lower the latency is going to be. And it also saves a lot of computational power towards the cloud, which eventually leads to saving a lot of cost. It's just a spiral, it's just a loop in itself. Simulation results confirm energy trades-off between devices. I just said that if, let's say, we have four cameras and four of them are just analyzing and processing their own videos, the amount of processing that might be eventually be in future required to process them at a single place, for example, EC2, if just sending all the data to the cloud, is going to be way higher rather than just actually dividing it to different places and simultaneously they are just processing their data. So no single server requires to process everything. That eventually helps a lot, and if it's a IoT device, it's already connected to whatever source of energy it is using. So yeah, the processing power and the hardware can be just present there, and it can do, which will eventually reduce the latency and the time taken. Latency is the time taken for the processing, and also money, as I just mentioned. So that's all from my side for this project. That's what I have done. Everything will be attached with the report that I will be submitting. So yeah, thank you for the watch. Thank you for watching. Hopefully, I'm clear that what I have done.